Hello all, today we are talking about chapter 4. This is Biomechanics part 2. And today we're going more into Newton's laws and looking at levers. All right, here we go. Newton's first law of motion, also known as the law of inertia, states that an object at rest will remain at rest and an object in motion will continue moving with a constant velocity in a straight line unless acted upon by an external force. This law describes the concept of inertia, which is the tendency of an object to resist changes in its motion. For example, a ball rolling on a smooth surface. If a ball is rolling on a frictionless or very smooth surface, it will continue rolling with a constant velocity in a straight line. In the absence of any external forces like friction or obstacles, the ball will keep rolling indefinitely. You can see here in the example with kicking the ball, of course, you're going to put it into motion, and it will continue in that motion with a constant speed and direction unless there is something in the environment that causes it to stop, such as a net, goal, score, go team. Newton's second law of motion describes the relationship between the net force acting on an object, its mass, and its acceleration. It states that the acceleration of an object is directly proportional to the net force applied to it and inversely proportional to its mass. Mathematically, it can be expressed as F equals m times A, where F is the net force applied to the object, m is mass of the object, and A is the resulting acceleration of the object. And for example, kicking a soccer ball. When you kick a soccer ball with a greater force, it will experience a larger acceleration and move faster. The force you apply to the ball determines how quickly it accelerates and changes its speed. The mass of the ball also plays a role, as a heavier ball will be more resistant to acceleration. And another example, in car acceleration, when you press the gas pedal of a car, the engine exerts a force that accelerates the car. The acceleration depends on the net force applied to the car and its mass. A larger force or lighter car will result in a greater acceleration, while a smaller force or heavier car will result in a smaller acceleration. The third law states that for every action, there's an equal and opposite reaction. This means that when an object exerts a force on another object, the second object exerts an equal and opposite force on the first object. Examples of Newton's third law of motion include when a person jumps off a diving board. The person exerts a force on the board, and the board exerts an equal and opposite force on the person, propelling them into the air. When a rocket is launched, the rocket exerts a force on the exhaust gases, and the exhaust gases exert an equal and opposite force on the rocket, propelling it into space. When a person walks, the person exerts a force on the ground, and the ground exerts an equal and opposite force on the person, propelling them forward, like you see in the picture on the right in the middle. Understanding Newton's third law of motion is important for exercise professionals who coach movement, as it provides a comprehensive understanding of the biomechanics and anatomy of the body. By understanding this law, exercise professionals can design workout programs that ensure the body is moving and strengthening in all directions. Momentum is the product of the mass and velocity of an object. It is a measure of the amount of motion an object has and is calculated by multiplying the object's mass by its velocity. It is a vector quantity, meaning it has both magnitude and direction. Linear momentum is defined as the product of a system's mass multiplied by its velocity. Momentum is directly proportional to the object's mass and also its velocity. Linear momentum is a measure of the amount of motion an object has in a straight line and is calculated by multiplying the object's mass by its velocity. An example of linear momentum can be observed in a collision between two objects. Let's consider a scenario involving a billiard ball and a stationary ball on a billiards table. Suppose the billiard ball is initially at rest and the stationary ball is struck by the cue ball, causing it to move. During the collision, the cue ball transfers some of its momentum to the stationary ball. During the collision, momentum is transferred from the cue ball to the stationary ball. Let's assume that after after the collision, the cue ball comes to rest and the stationary ball acquires a velocity. This example illustrates how linear momentum is conserved in an isolated system, such as a collision between two objects. The total momentum before the collision is equal to the total momentum after the collision, demonstrating the principle of momentum conservation. Angular momentum is also called rotational momentum and is the rotary inertia of an object or system of objects in motion about an axis that may or may not pass through the object or system. An example of angular momentum can be observed in the motion of a spinning top. A spinning top is a toy that consists of a pointed tip and a rotating body. As the top spins, it exhibits angular momentum. As long as no external torques are acting on the spinning top, the angular momentum will remain constant. This is known as the conservation of angular momentum. Even if the spinning top tilts or wobbles, its angular momentum will stay the same as long as no external torques are applied. The example of a spinning top demonstrates the concept of angular momentum and how it can be calculated based on the object's moment of inertia and angular velocity. Angular momentum plays a crucial role in the study of rotational motion and is conserved in the absence of external torques. The transfer of momentum is where can transfer momentum from one object to another. For example, throwing a ball is a transfer from the legs to the torso to the hand, arm, and then the ball. Impulse is a term that quantifies the overall effect of a force acting over time. The impulse momentum theorem allows us to make a direct connection between how a force acts on an object over time and the motion of the object. An example of impulse can be seen in the action of kicking a soccer ball. When a player kicks a stationary ball, they apply a force to the ball over a short period of time, resulting in a change in the ball's momentum. The ball applied by the force over the short time interval results in a change in the ball's momentum. Impulse is directly related to the change in momentum of an object. According to Newton's second law of motion, the change in momentum of an object is equal to the impulse exerted on it. In this case, the impulse exerted on the ball causes it to gain momentum and move in the direction of the kick. The concept of impulse is important in sports and other dynamic situations where forces act over short time intervals to produce significant changes in momentum. By understanding impulse, athletes can optimize their techniques and apply forces more effectively to achieve desired outcomes. Torque is a concept used in physics to describe the rotational force that causes an object to rotate about an axis. It is also known as the moment of force. Torque depends on two main factors, the force applied and the distance from the axis of rotation at which the force is applied. It can be mathematically represented as torque equals force times moment arm, where T represents torque, F represents the force applied, and R represents the moment arm, or the perpendicular distance between the line of action of the force and the axis of rotation. The unit of torque is typically expressed in Newton meters in the metric system or foot-pounds in the imperial system. Here are a couple of examples. The external moment arm, let's consider the example of a person performing a bicep curl using a dumbbell. The external moment arm is the distance between the axis of rotation, which is the elbow joint, and the line of action of the external force, which is the weight of the dumbbell. As the person flexes their elbow to lift the dumbbell, the distance from the elbow joint to the weight creates the external moment arm. The longer the moment arm, the greater the torque applied to the joint. And I love the picture on the top right hand corner. Get a bigger wrench is really what it's all about. You want to increase that moment arm. So those people with long levers, long arms, long limbs can produce a lot of force. The internal moment arm can be observed in the human body when muscles generate forces to produce joint movements. For instance, during knee extension or straightening of the leg, the quadriceps muscles apply a force on the lower leg bone, the tibia, through the patellar tendon. The internal moment arm in this case is the distance between the knee joint axis and the line of action of the muscle force. The magnitude of the torque generated by the quadriceps depends on the length of the internal moment arm. In both examples, the moment arm influences the torque or rotational force around a joint. A longer moment arm results in a larger torque, while a shorter moment arm produces smaller torque. Understanding the moment arm is important for optimizing exercise technique, assessing joint loading, and analyzing biomechanical movements. And in all cases, get a bigger wrench. Lever systems are mechanical devices consisting of a rigid structure that rotates around a fixed point called the fulcrum. They're commonly used to amplify or change the direction of a force applied to one end of the lever to produce a desired effect at the other end. And you can see that in the example here. You have the long arm, that's the lever, and then the fulcrum is the point of axis of rotation. And you have the force that's being applied by the ball on the left-hand side. An axis of rotation, also called an axis of revolution, is a line around which an object rotates. Joints are an example of an axis of rotation. Applied force refers to a force that is exerted on an object by an external agent or system, like the ball. It is a physical quantity that describes the push or pull applied to an object to cause a change in its motion or deformation. Applied force can be categorized based on its direction, magnitude, and point of application. Here are key points about applied force. The direction of an applied force is the line along which the force is exerted. It can be vertical, which is what you're going to see here in the diagram, horizontal, or at an angle relative to the object being acted upon. The magnitude of an applied force is the strength or intensity of the force, so it would be the mass of the ball. It is typically measured in units of force, such as newtons in the metric system or pounds in the imperial system. The point of application refers to the specific location on the object where the force is applied. It can be a single point or distributed over an area. You can see here it's on the left-hand side of the lever. An applied force can cause various effects on objects, such as changing the object's state of motion, accelerating, decelerating, or changing direction, or deforming the object's shape or structure, or stretching, compressing, or bending. Applied forces can be contact forces, such as pushing or pulling an object with direct physical contact, or non-contact forces, such as gravitational or electromagnetic forces that act from a distance. In this case, the ball is going to exert a gravitational effect, pulling the fulcrum, pulling the lever down on the left side. Examples of applied forces include pushing a car to make it move forward, pulling a door to open or close it, kicking a ball to set it in motion, and lifting weights at the gym, pushing a shopping cart through a store. Understanding applied forces is fundamental in the study of mechanics and physics, as they play a significant role in describing and analyzing the motion and behavior of objects. The principles of applied force are relevant in various fields, including engineering, sports science, and everyday life situations. Resistive forces, also known as opposing forces, are forces that are acted in the opposite direction to the motion or intended motion of an object. These forces arise due to interactions with the surrounding environment and tend to hinder or slow down the object's motion. Resistive forces can vary depending on the nature of the object, the medium through which it moves, and the specific conditions. Here are a few examples of resistive forces. Frictional force is a resistive force that opposes the relative motion or an attempted motion between two surfaces in contact. It arises due to the roughness or interlocking of surface microstructures. Friction can impede the motion of objects that are sliding, rolling, or moving through a fluid medium. Oftentimes you'll see that with skating, that you're creating friction. I'm thinking ice skating or rollerblading, either one. Roller skating, you're using friction in order to cause motion. Air resistance or drag. When an object moves through a fluid medium such as air or water, experiences a resistive force known as air resistance or drag. Air resistance opposes the motion of objects moving through the air and increases with the speed and surface area of the object. Today, if you were to go outside and walk, the wind's blowing about 30 miles per hour, it would cause some resistance, air resistance or drag, depending upon which direction you're walking in. If you're walking into the wind, it's going to cause resistance. Otherwise, if you're walking in the opposite direction, it's going to help you. A buoyant force is also a resistive force, and tension as well as magnetic and elastic resistance. Understanding resistive forces is crucial for analyzing and predicting the motion of objects, designing efficient systems, and overcoming or minimizing the effects of these forces when desired. In various fields such as physics, engineering, and aerodynamics and sports science, accounting for resistive forces is essential for accurate modeling and practical applications. Lever systems are categorized into 3 classes based on the relative positions of the force, fulcrum, and load. This is an example of a first-class lever, the forearm, where you're extending the elbow against resistance. A first-class lever is a simple machine consisting of a rigid bar or beam that pivots around a fulcrum, or the elbow, or pivot point. In a first-class lever, the fulcrum is positioned between the applied force and the load or resistance. This arrangement allows for various applications and mechanical advantages. The axis is located between the resistive and applied forces. Again, with like a triceps extension exercise, the axis is the elbow joint, with the applied force being the triceps on the olecranon process, and the resistive force is the weight. A second-class lever is a simple machine consisting of a rigid bar or beam that pivots around a fulcrum or pivot point. In a second-class lever, the fulcrum is positioned at one end of the lever while the load or resistance is located between the fulcrum and the applied force. For example, a calf raise exercise. The axis is the ball of the foot, while the applied force is the gastrocnemius or calf and Achilles tendon on the calcaneus. The resistance force is the center of mass of the body. Other examples of this are the seesaw or top of a hammer to get out nails, oars, or scissors. In third-class lever, the force is applied between the fulcrum and the load. This configuration results in a mechanical disadvantage as the force arm is shorter than the load arm. Third-class levers are common in the human body, such as the forearm acting as a lever with the elbow joint as the fulcrum and the biceps muscle exerting the force to move the load, as in picking up a dumbbell. Here you see in the example, the applied force is located between the axis and the resistive force. So with the bicep curl, the axis is the elbow joint. The applied force is the biceps on the ulna, and the resistive force is the external dumbbell. And all 3 classes of levers, the effectiveness of the lever system can be determined by the relative length of the force arm and the load arm. A longer force arm compared to the load arm provides a mechanical advantage, following the application of a smaller force to move a larger load. Conversely, a shorter force arm results in a mechanical disadvantage, requiring a greater force to move the load. Understanding lever systems is essential in various fields, including engineering, biomechanics, and everyday applications. By manipulating the position of the fulcrum and the lengths of the force and load arms, lever systems can be optimized to achieve desired mechanical advantages and outcomes. And that is all that I have for you today. Be looking for part 3 of biomechanics in our next session. I'll talk with you soon. Have a great day.